right, so good morning. Thanks for joining our CBCS seminar for Tuesday. This morning we have CBCS's Deputy Director, Dr. Nathalie Butt, and this morning she's going to be speaking about using traits to inform marine species vulnerability, and in particular the comprehensive assessment of how species and ecosystems are impacted by anthropogenic stressors, and are critical for guiding conservation and management investments. So without further ado, thank you so much, Nathalie.
Thank you. I'll just attach the microphone. Okay. Thanks everyone for zooming in or joining us in person for our first in-person talk for a while. So I'll share my screen. I'm going to talk about what Mercedes just said, so about trait-based vulnerability assessments and how it's important to use all the information we can when we're planning conservation actions, and using trait information is important in that way. And I'll talk a little bit about anthropogenic stresses as well. Before I do that, I just wanted to acknowledge the traditional owners of the land on which I live and work, the Yagara and Turrbal people, and pay my respects to their leaders, past, present, and emerging. So as we know, marine species, as with species and ecosystems everywhere, are subject to anthropogenic threats and pressures, and lots of conservation action and management actions aim to help protect them from these. But one of the things that we don't always know about, or we don't always delve into, is how the species are actually responding to those stresses. So previously there have been some global assessments done on habitat vulnerability, marine habitat vulnerability, but because species respond differently to stresses, it's actually quite useful to know how individual species are going to respond. And so that's why we're looking at traits, individual species traits, and I'll take you through all that. Before I go into that, I'm just going to have a big segue. Actually, I wanted to just pay tribute to Mr. Whiteway, who was my high school geography teacher back in the 1980s in Melbourne. And he was an amazing guy. He'd been living and working in the area of Beaumaris, which is a few kilometers south of Melbourne, for decades. And he was really keen ecologist and naturalist and environmental advocate and conservationist before most of us even knew what that was. And he fought for decades to get a marine reserve gazetted at Ricketts Point, which then he was successful in 2002. And it became Melbourne's only marine sanctuary. And in fact, I don't know if it still is now, but at the time it was. And in fact, one of the few near a big city, a capital city anywhere in the world. And then he was, in 2013, he received the Medal of the Order of Australia for his work. And as he's he was a humble and generous person, so he insisted on mentioning the other people that had been involved. Our school, he taught at Beaumaris High School, or Bowie High, from 1965 to 2007. And we were about a kilometre away from the beach, and so we'd often go down there for geography classes and learn about, be on the rocks or in the shore, in the water's edge, learning about ecology and geography. And that was a fantastic, a wonderful opportunity for all of us, and all of us who got to experience that. And I'm sure that has contributed to my love of natural science and understanding of the world. And I think he'd be quite interested in this project, looking at vulnerability and marine species and stresses. So I will start by explaining what we're defining as vulnerability here. So there are several components to a species vulnerability to a threat or a stressor. There are intrinsic traits or biological characteristics which determine a species sensitivity, which is how much it's affected or impacted by a stressor or a threat, and its adaptive capacity, which is how well it responds to or recovers from a threat. And those are the intrinsic internal traits. And then there's also another factor, which is exposure, which is an external thing. And that's actually the threat or the stressor itself. And that's about where the threat exists and where the species exists if they're in the same place. So obviously something that's not exposed to a stressor is not going to be vulnerable to it. Okay, that's all I wanted to say about that. And we can think about how sensitivity and adaptive capacity interact to drive trait-based vulnerability. So we can think of it as sensitivity is moderated by a species' adaptive capacity. And where we have species that have low adaptive capacity and high sensitivity, they're probably not in a great place in terms of persisting, population persistence. Where we have species that are sensitive but have a higher adaptive capacity, then there's a greater probability of persistence. And what we can try and do with management actions is to enhance adaptive capacity. So something that might have low adaptive capacity but also low sensitivity might be worth us spending money on trying to improve its adaptive capacity through habitat management or whatever. For example, the short-tailed albatross is threatened and has lost a fair amount of nesting habitat, but its overall range is really large. So by transplanting young albatrosses, which are super cute, onto different islands or places in its overall range, then population resilience can be enhanced. Conversely, the polar bear is obviously highly sensitive to climate change and has a super low adaptive capacity because it can't live anywhere else. So finds itself in the wrong quadrant for survival here, unfortunately. So what did we do? How did we translate all that trait information, species information? How do we actually translate that into a framework that we can then calculate species vulnerability, and then how can we actually apply that in a useful way? So what we did was a 3-step process, which started with gathering expert data, literature review data, trait information for marine species. And then we populated a trait database. I'll go through all this in detail in a minute. And then we also built a stressor trait matrix where we scored every trait with every stressor. And then we developed a vulnerability model, which is how we calculated vulnerability scores for everything. So the first step was a species expert workshop, and you'll probably recognize some of the people in the photo there. Oh, I should have said at the beginning, the project was a joint project between UQ, led by Carissa Klein here, and the University of California, Santa Barbara, led by Ben Halpern, who many of you know. And we had taxonomic experts from all around the world came to the workshop. So we had people came from Canada, Ireland, the US, and some of us from Australia. And as well as anything else, this was actually the last trip for most of us because it was in mid-February last year. So we were really fortunate to have got that trip in before travel everywhere shut down. So the experts were experts in different taxonomic groups. So we had somebody there who was an expert on corals, we had seabirds, marine reptiles, bony fishes, sharks and rays, echinoderms, which are invertebrate species like sea cucumbers and starfish, and some other things between them as well. And later on, what we did was actually reached out to other experts recommended by these to cover any gaps that we had with our major groups. So during that workshop, thinking about different anthropogenic threats, we came up with a list of 42 traits that were important or are important for species vulnerability. And we grouped these into 5 trait groups. So we had movement, reproduction, specialization, spatial scale, and biophysical traits. So the movement traits were related to adult mobility, planktonic larval duration, or PLD, which is apparently the known acronym for that. I don't know anything about marine species apart from turtles. So reproduction, we had strategies, we had fecundity, population size, if something was affected by sex ratio in terms of temperature. So for reptiles, as we know, if it's hotter for the eggs, then there are more females than males, so that kind of thing. For specialization, it was mainly about physiological tolerance breadth. So we looked at temperature and salinity and oxygen and pH, whether something was a photosynthesizer or not, which obviously only applies to corals really, whether things existed at the air-sea interface. So if things had to come up to breathe, for example, or if things were floating at the air-sea interface all the time. We looked at habitat dependency, interspecific interactions and breeding ranges. The spatial scale was how far a species range extended. We also looked at what depth it occurred at and what oceanic zone. So if it was close to the coast or out in the middle of the ocean or somewhere in between. And then the biophysical traits were about body mass, about calcium carbonate structures, if they had communication requirements, sound or navigation requirements, what respiration structures they had. So you can imagine something with lungs is going to be quite different in terms of vulnerability to certain anthropogenic stresses than something that's a filter feeder. So yeah, so we had 42 traits for those. And then after we'd made the trait database, we then developed the trait stressor matrix. So we first of all had to come up with a list of 22 anthropogenic stresses that we thought were tractable to deal with in this framework. And these were actually based on some work that Ben Halpin and others did a couple of years ago, looking at habitat vulnerability. So we had a range of stresses, and they all relate to climate change or ocean-based threats or land-based threats, fishing, and I can't remember what the last one, infrastructure perhaps. Anyway, that doesn't matter. So we came up with these 22, and most of them actually fit within 3 broader categories, which are pollution, climate change, and fishing or biomass removal. And then what we looked at was developing the trait stressor matrix. And this is actually a very small snapshot of just a couple of traits and trait categories within each trait. So we had 42 traits, but within each of the traits, we divided them into categories. So for example, the biomineral trait had 7 different options for the expert filling in the spreadsheet for each thing. And then we scored for each stressor. In this case, it's for inorganic pollution. We scored between none, low, medium, and high for each of the trait categories, and whether or not we thought it would be medium sensitivity or low sensitivity or no sensitivity. And again, we used expert knowledge for that, and literature review, and yeah, that was quite a long iterative process, but we did that. And you can see how with 22 stresses and 42 traits, but all split up into different categories, we ended up with actually 2,500 individual scores for the trait stressor matrix. So every single one of those was researched and decided upon that would be. So I'm just really sort of not skimming the surface of what we've done, but there was a lot of data, tons and tons of data that's behind all of this. And I'm obviously summarizing what we did, but if anybody's interested or wants a project, we have loads of data, and there's loads of opportunity for developing different aspects of the work. So then we derived a vulnerability model. And as I explained previously, so sensitivity is basically modified by adaptive capacity. And then we also had an exposure modifier included in the model. So this wasn't exactly the same as looking at spatial exposure, which is going to be the next stage of the project when we can actually map species distributions and stresses. So that will sort of be another layer for exposure. But this was what we're meaning by exposure modifier was, for example, in the depth zones. If a species occurs in a certain depth zone, but the stressor isn't there, then there won't be any vulnerability, or there won't be any immediate impact to that. And that's it written in words, but obviously there's a fancy equation, and which I'm not going to go through in detail, but if anybody's interested in the maths behind it all, flick me an email and I can send you the several pages long development of the model. And then we had, so the experts provided us with trait data at different levels. So a lot of it was species level trait data, and then some of it was genus level trait data. And in some cases, the species data was actually representative of the whole genus or even the whole family, or even an order in one case for the sponges. So, which is an invertebrate group. So what we did from those initial species trait data, we were able to gap fill to higher levels. And this gave us over nearly 31,000 species that we had represented with direct data. And then we were also able to then gap fill downwards, for example, where we used, we assumed that congeneric species had the same traits. So we were able to come back down the tree. Well, I was going to say something else about that. So we ended up with 44,000 species in total, and that we had representative data for. And then what we did was scraped the worms database, which is the world of marine species. Well, oh no, I can't believe I've forgotten what it is. Anyway, we'll get to that in a minute. Yeah, so then we were able to scrape the worms database, and for each of those species that we had represented, then we were able to match them. So we ended up with, as I said, over 44,000 species, which is quite a lot. And then after running the models for each of those species, and then this is the, sorry, it's a little bit small. I just wanted to show you the whole overview. Oh, I should have mentioned earlier on the 12 taxonomic groups that we developed the framework were seabirds, marine mammals, bony fishes, reptiles, elasmobranchs, which are the sharks and rays, mollusks, which were bivalves and gastropods, snails and stuff, corals, echinoderms, which are the starfish and the sea cucumbers, cephalopods, which are octopus and squid, marine arthropods, which were crabs and shrimps and sea spiders, polychaetes, which are basically those little worms that live in the bottom of the sea everywhere, and sponges, which float around. I think I don't really know much about them, as I mentioned before. Anyway, so these results are grouped into vertebrates. So the first 5 panels are the 5 vertebrate taxa that we looked at, and then the other 7 are the invertebrates. And the stresses are ordered by decreasing impact. So biomass removal was the highest impact, running through pollution and bycatch and habitat dependency, all the way down to wildlife strike and invasive species, which were the least important of the stresses. I'm showing you this plot, but the framework we've developed, it gives a relative vulnerability, so between species and between groups and between stresses. But because some of the stresses aren't actually relevant for some of the species groups, it might be slightly misleading. So the red line is the average across that taxonomic group, but in some cases it's not really that well, not valid, but it's it could be a little bit misleading. And to actually look at an individual taxon or individual stresses that we may be interested in, we'll have to sort of like delve a bit deeper into the results. So we can look at, for example, the seabirds, which are 360 odd species of seabirds, and they were the most vulnerable of the vertebrate taxa, and that's because they're actually affected by stresses that are both on the land and in the ocean. So they're affected by light pollution, but also bycatch. So not many things. So that part of that would be because they have marine and terrestrial life stages, and they live across the more than one realm. And then for corals, mollusks, and echinoderms were the most vulnerable of the invertebrate groups, and they were particularly vulnerable to the interaction, well, not really the interaction, but ocean acidification, but that's also influenced by ultraviolet and temperature. So they're vulnerable to that, and that's partly because of their calcium carbonate structures, or largely because of their calcium carbonate structures, which, as we know, are becoming more problematic for them to develop when the ocean is more acid or if it's hotter. And then if we look at marine mammals, we can see that for them and for the other large marine vertebrate species, biomass removal was the most important stressor, as it was for everything. I'll talk about that a little bit in a minute. But the other ones related to fishing, such as bycatch and macroplastic pollution, which is where something becomes entangled, were also important stresses. And the marine mammals were had the highest, I think they were one of the highest with wildlife strike as well, which is where boats and ships come along and bash into something. So yeah, with the fishing, that was a slightly different stressor to some of the other ones, because it's driven by what humans target for fishing. So even though we had very high scores for biomass removal for all of the taxonomic groups, it was the highest or the most important stressor. That doesn't necessarily mean it's having the most impact now. So for example, for marine mammals such as whales, previously it would have been a high impact as well as a high vulnerability, but as they're not targeted by humans at the moment, then it's actually a low impact, but still the potential vulnerability is high if you get the distinction. So for example, something like sea cucumbers, which are currently targeted by humans, there are lots of examples of fisheries or areas where they harvest sea cucumbers that have been completely they've been completely removed from those areas. And this shows the most four most vulnerable taxa in each of the key stressor groups. So we had the pollution-related stresses, fishing-related stresses, and climate change-related stresses. For the larger vertebrate species, the fishing-related stresses were the most important: biomass removal, bycatch, entanglement. And then for the small invertebrate groups, pollution was most important. So you can imagine that something that's small and sitting on the bottom of the sea is going to be affected by sedimentation more than something that can get up and move away. Also, because it breathes as a filter feeder, it's going to be ingesting more of that pollution. And then the climate change related stresses were more important for some of the more mobile invertebrate species. And again, this is just a very broad summary that we put together, but there's a lot more detail available if anyone's interested. So that's all. Oh, yes. So then we can look at how the individual traits and trait categories conferred vulnerability. So the things that were most important, so most of the trait categories conferred vulnerability or sensitivity to water temperature, air temperature, inorganic pollution, and organic pollution. And again, if anybody's interested, we can go into like some of the individual traits and see how they relate to the individual stresses. So that's great. We've done that. We've developed a framework that gives us vulnerability scores for all invertebrates and vertebrates in the ocean. But what can we actually do with that? How is it useful for conservation? So it gives us much more information than we previously would have had, looking at how we can target and manage different species or populations. So we can use it to inform fisheries regulations to avoid or reduce bycatch. We can also pinpoint different places for protection, for example, species-specific foraging or breeding locations. It can help us guide reserve designs. Again, we can focus on breeding populations. That's really important for seals, for example, that need to have some rocks right by the shore to spend their time when they're breeding, but they don't use it all the time. It also enables a more precise targeting of protection, so we can avoid or reduce conflicts over where to locate conservation areas, which is always a problem when you have human amenity use as well, because we all like going to the beach and we all like walking along the coast and we all like swimming in the sea. So we need to try and balance those different uses of the area. So we can also look at designing movable protected areas for migratory species. So those can be movable in space and in time. So it can be at certain times of the year, it can be a protected area or a marine reserve or something. And then at other times of the year, it's open, and the same in terms of spatial protected areas. Also, it can inform global assessments to inform international conservation policy, such as the Convention on Biological Diversity and the UN Sustainable Development Goals, which are the basis of most national conservation policies. So there's a raft of potential applications for it. And it's a very flexible framework. It can be, if somebody is interested in a particular region of the ocean, or a particular ecosystem, or particular threatened species, or specific stresses, they can use the framework to come up with some relative vulnerability, and that can help them prioritize what they want to do in terms of managing those stresses, to either look at species-specific protection or to see what would give them the most bang for their buck in terms of what would protect the most species in their region or area. I think that's mainly that. I'll just end with a few caveats. Yes, we'll register with marine species, that's it. We did have a lot of species in there, just over 44,000, and that's not quite 20% of all of the species on the WERNS database. So obviously, there's a lot missing, and we weren't able to capture everything. But again, that can be something that can be expanded in the future, because the framework is flexible and adaptable and updatable. We focused on vertebrate and invertebrate animal species. So we haven't covered marine plants such as seagrass. We haven't covered algae such as giant kelp or other seaweed. So that could be a good target topic of research for someone who's interested in a project. The framework as it currently is doesn't capture the temporal aspect of vulnerability. So it doesn't differentiate between ongoing sensitivity or impacts, such as climate change, which are projected to become greater, the impacts or the threat, and temporary sensitivities, such as entanglement, which is a sort of one-off, or wildlife strike, which is a one-off thing. And we know that some species that aren't currently showing that they're particularly sensitive or vulnerable to some of the climate change factors probably will be over time. Similarly, we didn't capture life stage variation in vulnerability. So things that have, say, a larval state might not be affected as an adult, but a particular stressor might affect them as a larva. So again, that's something that can be maybe developed and included at a later stage. We looked at direct effects of stresses on species. So we didn't look at indirect things, for example, where a particular species depends on a particular food species, and if that food species is somehow affected by a stressor, then that will affect the food availability for the species that we're interested in. But we didn't have the capacity at this point to do that, so we've just looked at direct impacts on the target species. We also, the anthropogenic stress is a very complex, I could have talked a little bit more when I was introducing the list about pathways, so they can come from different, one stressor can have several different pathways. For example, the organic pollution one can come from runoff, it can come from infrastructure or waste. There are lots of different processes that can lead to that. And obviously lots of them will interact with each other as well, and we weren't able in this iteration of the framework to capture interactions between the stressors. The traits that we use also had to be quite broad because we were trying to capture, we had to have enough traits in there and trait categories to capture the whole range of the vertebrate and invertebrate species that we looked at. But they had to also be general enough that they could be applied to, or everything could be incorporated in that database. However, having said all that, it's actually quite, it's a robust framework. It's pretty tractable. It makes sense. We did some various sensitivity testing and calibration testing, taking out some of the species, especially when we did the gap filling of species, to check that it didn't skew the results too much. So it's a pretty robust and tractable and reasonable attempt at a global framework. And at the moment, it is a global framework. So that was what we did. And it's hopefully going to be accepted and published quite soon in Ecosphere. Obviously, I didn't do this work myself, so the photo again of the workshop team, and then plenty of other people who joined in again later on. And that's pretty much it, I think. So thanks for listening, and if anyone has any questions or a burning desire to find out more about it, now's your opportunity.